Hello, I'm Hyeongheon. In this video, I'll introduce our paper, Snap Low Latency Test Annotation with Sparse Update. Just like a quick snap, it updates only at a sparse intervals instead of every batch, sharply reducing latency without hurting accuracy. Starting with the motivation. Deep learning models often suffer performance degradation under domain shifts where the target data differ from the source data. These shifts naturally arise after deployment due to real-world factors such as lightning chains, weather, noise, and other dynamic conditions. Test annotation addresses this by updating the model online after deployment without accessing the source data. While recent TT algorithms have advanced in complexity to improve accuracy in dynamic scenarios, most of them are designed for server-level resources and overlook the computational limits critical for real-world deployment. State-of-the-art TTA often introduce heavy overheads such as multiple backpropagations and augmentations, resulting in 2 to 30 times higher latency than inference only. This extra cost is rarely considered, making this method impractical for real deployment. This becomes even more problematic in real scenarios where data streams rapidly and continuously. If adaptation is slow, the model lags behind incoming data and starts missing new samples. To address this, we consider the sparse TTA setting where the model deliberately skips updates. For example, adapting only once every 3 batches. This reduces latency but also limits available samples and updates, making accurate adaptation much harder. So, how can we adapt sparsely without losing accuracy? This is where Snap comes in. It has 2 key modules. One is class and domain representative memories, which selects a compact representative set of samples for effective sparse update. And the other is influence-only batch-aware memory normalization, which stabilizes normalization between updates by blending memory statistics with recent inference batches. Now let's move to the first module, CNDRM. Under sparse updates with submitted data, the key challenge is selecting the most representative samples for adaptation. To do this, we rely on 2 complementary criteria. First, we favor high-confidence samples while maintaining prediction balance. This prevents error propagation from incorrect store labels and keeps adaptation stable. In addition, we estimate how well each sample reflects the target domain by measuring its ascertained distance to the domain centroid. This lets us retain samples that best capture the current distribution. With these 2 signals, CNDRM maintains a compact but adaptive memory. The memory size matches the batch size for efficiency, and when it becomes full, we replace the samples far from this domain centroid with new, high-confidence ones that better satisfy both criteria. As a result, the memory consistently keeps the most representative samples under shifting distributions with minimal overhead. Between sparse memory-based updates, the model must rely only on normalization to track distribution shifts, but limited memory statistics can drift from each new batch. IOBML fixes this by anchoring normalization to stable representative statistics and lightly adjusting them using recent inference batches. This balance keeps the model robust while still adapting and results in much more stable performance under sparse TTA scenarios as confirmed in our ablations. Taken together, 2 components operate jointly to enable efficient and accurate sparse adaptation. Now let's see the result. Across multiple datasets and the state-of-the-art TTA method, Snap consistently reduces latency while maintaining accuracy. And this efficiency generalized across different adaptation rates, VATs, and real edge devices, showing Snap is practical beyond controlled benchmarks. Further experimental validation and in-depth discussions are provided in the main paper and the appendix. To summarize, Snap tackles the latency accuracy trade-off in TTA by stratifying update and leveraging representative samples. It significantly reduces adaptation latency while preserving accuracy across diverse TTA methods, models, datasets, and edge devices. For further discussions, please visit our poster or reach out using the contact information. Thank you for listening.